we're going to be looking at exponential functions. With exponential functions, we first need to talk about the exponent rules. There's a couple different exponent rules. To start off with, anything to the power of 0 is going to equal 1. If you have a to the power of m times a to the power of n, you're going to add those exponents. Instead of multiplication, let's say that you have division. If you have division, then this is really subtraction of those exponents. If you have a to the power of a negative number, in this case, I'll just use an example with -2. This is really, remember, if you have a negative exponent, it flips it. So in this situation, our exponent is in the numerator, so it would go to the denominator. So we have 1 over a to the power of 2. If you have something raised to a power, then you're going to have multiplication. These are your exponent rules, and the reason why we're going through this is because we want you to understand these rules when we get to solving exponentials and talking about logarithms a little bit further in depth. So just like I said, just wanted to touch base, make sure we're fresh on that. So now let's talk about an actual exponential function. So an exponential function is in the format of y equals a times b to the power of x. And with that being said, a is your initial amount, and b is your growth or decay factor, depending on your situation. If your b value is between 0 and 1, then it's decay. If your b value is greater than 1, I know I just put that the wrong way. If it's greater than 1, then you have a growth. So remember that with an exponential function, you're talking about something like doubling or cutting in half, okay? So something to note, a little bit of discussion of, what's a linear function versus a exponential function. Remember that with a exponential function, you're going to do a ratio. So the previous term divided by the current term is going to give you that ratio. So f of x plus 1 over f of x is going to equal your growth or your decay factor. Okay, so that's easier to look at with an example. I understand that, but it would be something of the nature f of 3 divided by f of 2 is going to be your growth factor. Okay, so just the notation of that, I understand it looks a little goofy. So then we get into, what does this look like graphically? So the properties of our exponential growth functions versus the properties of our exponential decay functions. With an exponential growth function, there are a couple different properties you need to know that are going to be important. Your domain is going to be negative infinity to positive infinity. Your range is 0 to infinity, aka it has a horizontal asymptote then at y equals 0. The y-intercept is at 0, 1. There are no horizontal ones, so I'm not going to list that. And it's increasing. So let's just look at a graph here real quick, just draw a rough sketch. That is an exponential growth function. So now notice we've got exponential decay. So similar properties, your domain is still negative infinity to positive infinity. Your range is again 0 to infinity. Horizontal asymptote, y equals 0. The y-intercept is still at 0, 1. But graphically, if it's decay, your graph is going to decrease. So exponential decay versus growth. Oh, might want to put this on here as a refresher. If you're in that format of y equals a times b to the power of x, for growth, b is greater than 1. For decay, your b value is in between 0 and 1. You don't ever have to worry about the negatives. The negatives are dealt with in the your reflection, so you don't have to worry about that. That's part of the transformation piece of it. Whether it's exponential growth or decay, that will take that out of there. So speaking of transformations, knowing our background of transformations, how do we graph this? So let's first just talk about the graph, or talk about what's going on here before we even talk about graphing it. So domain on this one is still going to hold true of negative infinity to positive infinity. My range, so thinking about my range here, my range is normally 0 to infinity, but I have this plus 2 at the end, so I know that that's going to drop my graph down 2. So now my range is going to be negative 2 to positive 2. My horizontal asymptote aligns to that range, so it's now y equals negative 2. And the y-intercept is also going to be shifted down because of that 2. I also have another component within this, and that's the negative x. That negative x there is just going to reflect it over the y-axis. So we have a reflection over y, and then we also have that graph shifting down too. All right, so let's talk about the graph now. So I'm going to draw my parent. So my parent function would be 3 to the power of x. It's still going to hold true of those properties from above. So now I'm going to graph the function I'm supposed to have. So 1, it's going to reflect over the y-axis, and 2, it's going to shift down 2. So my horizontal asymptote here is now going to be at y equals negative 2. Again, this is just kind of a rough sketch, but you're getting the idea behind the transformations. Just as a double check here, I've already got it pulled up on Desmos. You can see graphically I'm at 0, negative 1. The graph did in fact shift down 2 because I can see my horizontal asymptote there at negative 2, and I can tell that it reflected over. So just talking about those transformations, we've been dealing with transformations since Algebra 1, but just going through it again. There's 2 other things to talk about when dealing with exponential functions. The letter E. E, remember, is a number. That's value is 2.718. This is you're going to see this in a variety of different ways. Generally speaking, you're going to deal with the e when you're dealing with logarithms as far as that natural log. However, e is just a number. It's no different than y equals e to the power of x. It's just an exponential. This is just telling you your growth amount. It's a specific number. It really doesn't come into play as far as like anything shifting whatsoever. It's just a number, but just something to note. The next thing is to solve the exponential equation. So when you have an exponential equation and you're trying to solve for x, this is not using, for right now, you are not using logarithms. The key here is to make the bases equal. So for instance, we've got this 4 and we have that 8. Can you rewrite it so that those bases are the same? The answer, of course, is yes. If I rewrite the 4, I can rewrite it as 2 to the power of 2. But because of my exponent rules, I still have that 2x minus 1. On the 8, this can be written as 2 to the power of 3, and again, drop down that x plus 3 using my exponent rules. Now, since I have the bases the same, we are going to cancel the base and solve for x. So now, if I cancel the base, this is gone, this is gone. I now have 2 times 2x minus 1 equals 3 times x plus 3. And I'm just solving for x. And I get x equals 11. You can always sub it back in and do a check, but just something to note on that. And last but not least, an application problem here. So the price P in dollars of a Honda Civic that is X years old can be modeled by the function P of X equals 22,683 times 0.85 to the power of X. So what was the initial value of the car? So remember, if we're in that format of y equals a times b to the power of x, a is the initial amount. So our initial value here is that 22,683. So thinking about, before getting to part B here, thinking about the rest of the equation. The 85, that's representing how much your car is depreciating. So thinking about this, the car is depreciating by 15% every year. Now you're probably asking, how did you get 15? So remember, this is 1 minus that rate. And so that rate is that 15%. You could also go the other direction and have it as 1 plus r, depending on what you're dealing with. In this case, we have depreciation, so it's going to be 1 minus. But just something to think about when you're looking at the whole equation. What do each of these numbers mean? For part B, how much should a 7-year-old Honda Civic cost? All you're doing is plugging that 7 right into the equation. And I'm sorry, I actually was not thinking, and I should have been prepped in advance to calculate that. My fault. We're going power of 7, and we get $7,271.65. Sometimes you'll be asked the other way. You might have like we'll just add this in here, a question C. How many years did it take to reach, say, $10,000? Okay, this question might come up And as of right now, we're not using logarithms. So the only way that you can actually do this is either guess and check or graphically using Desmos. So I'm going to show you how to use Desmos for this. So we know that our equation is that 22,863 and 85. 63, 6. Got my 6 and my 8 mixed around, sorry. Okay, so you're not obviously going to see it on the graph. You're going to have to zoom out, right? So we want it to be 10,000. If you want it, thinking about that's the y. That 10,000 is the y. So we're going to do y equals 10,000. Zoom out really far here and zoom back in. You're just trying to find that intersection point. Where does y equal 10,000? And you already have the graph. So looking at this graphically, find the intersection point, and it's going to be 5.04 years. Okay, so graph the original, graph y equals 10,000, find the intersection. Again, we will later on go through and I will show you how to actually solve this using logarithms. You've done it before in Algebra 2, but you might not remember it, and that's totally fine. Just one of those things that we'll have to get through. So this is just a intro into exponential functions. We'll obviously dive deeper into this when we start talking about modeling and that kind of stuff.